If during your system design interview, your interviewer asks you how to handle a massive traffic spike and you use the term rate limiting and load shedding interchangeably, you might have just scored some negative points in that system design round. Most candidates confuse the two, but knowing the difference is important. We all know we need to protect our services from being overwhelmed, but the question is, should you reject based on who the user or client is or based on your current health of a server? The answer determines whether you need a rate limiter or a load shedder. So, hey everyone, today we'll be learning load shedding and rate limiting and the differences between two. So, let's start. So, as load increases on a system, it should automatically scale up, right? So, this is the very first thing we do. The simplest way to do is to add more capacity to your servers, right? And scale it horizontally rather than scaling it at vertically. For services that adopt a serverless architecture like uh, Google Cloud Functions or AWS Lambda, horizontal scaling happens nearly instantaneously as capacity is to just spun up on the demand to handle the work. For non-serverless services, it takes a little longer to autoscale. Typically, even scaling within minutes is fine. However, what happens if load increases on a service faster faster than the auto scaling can add the capacity? So what happens in this situation? The service has only two options. Like the service has only two options. The very first option is to get overwhelmed and slow down all the requests. And the second option is it can shred the excess request that comes to your system and only pass the important ones or maybe more critical requests, and hence maintaining consistent performance for the request that it does take on. So mostly everywhere the option 2 is chosen. So we greatly prefer maintaining consistency overall, predictable performance, which is the option 2, especially during any overload situation. So adding increased latency to an overload situation, which was the option 1, can cause ripple effect in the distributed system that can spread the impact to other system and it can lead to global outage. But the fail fast strategy that we have in the option 2, it helps overload system continue to make progress and do some useful work. So that means option 2, we are trying to keep our service alive. So it means we never want our service to die. Still make some progress rather than completely shutting down. So with this situation and this solution, we have found that load shedding is one useful tool for dropping excess load in an overload scenario. So now we can define what load shedding is. It is an act of cheaply rejecting work instead of spending limited resource that we have in our CPU on it. So for an HTTP service, load shedding means retaining an immediate error, maybe sending back a 503 status code saying that service is unavailable, right? An example is very simple. Maybe during a event on Book My Show, one, like the users are rattling going behind and trying to book the ticket, right? This can cause thunderherd problem, a very classic example where server can easily get overwhelmed. Now when we implement and when we do load shedding, this help the system to buy some time for auto scaling. Since the alternative to returning an error code becomes slow for all the requests, we shouldn't do that. So in the situation where we have a server handling multiple tenant, or you can say client A, B, C, D, E, F. This is typically known as multi-tenant architecture, where a single instance or a single server is trying to cater multiple clients or multiple tenants. So in a multi-tenant service, load shedding is sometimes not enough to make the multi-tenant service appear as a single tenant service to each customer. So what does this mean is every client should should be isolated, as in every client should feel as if they are the independent client to the server. Typically, load from multiple tenants is unrelated, like they are not correlated. So that is, each customer has its own use case and request rate. Maybe client A must be sending 10 QPS. So QPS is nothing but query per second. Some other terms like TPS or like OPM, operation per minute. So these are the different terminologies we use while talking about systems and the request within the systems and the client. So typically load from multiple tenants is like unrelated. Therefore, if the overall load increases abruptly on a service, so let's say we somewhere B is sending 1k QPS and C might be sending let's say 20 QPS, let's say 100, 150 or maybe 1 QPS. So therefore, if the overall load increases abruptly on a service, that increase is most likely driven by a single tenant. Here we can see the client is B is trying to send a lot high QPS compared to the other clients. With keeping fairness in mind, we want to avoid such failing numbers because these number of requests are crosses all the tenant in response to an unplanned load increase from a single tenant. Might be like B is sending more traffic and this could be a spike. But on an average, the traffic that B sends to our service would be maybe 100 on an average, but there could be a spike or maybe unplanned load from the single tenant. To add fairness to this multi-tenant system, now we use rate limiting to shape the unplanned increase in the traffic. So we enforce quota to each of the client. Quota here is nothing but the maximum value for the resources that we provide or give to each client, like per tenant or maybe you can say per workload. Yeah. This way, if the multi-tenant service experiences unplanned increase in the load, the unplanned portion of that workload is simply rejected. Let's say client B is a very high reputation customer or very important to our service. We can say, okay, we'll give 500 QPS, 500 QPS as a quota. So all requests above this 500, like the next 500 month request will be rejected because other requests are going above the quota. Like load shedding, enforcing rate-based quota involves like cheaply sending an error response instead of handling that request. However, this response indicates that the client has exceeded its quota, not that the server is out of capacity, right? So this never means that server is down or crashing or throttling. It simply means that whatever quota was assigned to a client is trying to abuse it, is trying to overuse it. So we'll simply send back to client B. This also will simply send back 429 status code. So this status code is for API rate limit exceeded, right? So this response indicates that the client has exceeded its quota. Client B has exceeded its quota, and we are asking them to retry. And maybe client B can have different like retry mechanism. Here he could retry maybe based on exponential retry or maybe exponential back off. Maybe client B can, okay, for him it would be okay, I'll wait for 1 second, then 2 second or 3 second. No, this not gonna work because if the client is rate limiting our server and there's no more quota, so this makes no sense to retry, right? So it simply should stop retrying as well. But in the case of server throttling, we can have a sort of mechanism where client can do some sort of exponential backoff retry because we are sending 503 status code when our server are when our servers are throttling. So in situation, we'll say client can have some sort of exponential retry where they will retry after every 1 second, 2 second, 4 second, 8 second, etc. Cool. So in rate limiting, we have uh, two different fairness strategies or maybe two different mechanism we use in rate limiting to implement one is called local fairness and the other is called global fairness. So local fairness refers to a mechanism that ensures that clients sharing a single, that means local rate limiter instance on the server or in a pod. Let's say you have different instances running or across a cell or a cluster. So each instance will have a sidecar of the rate limiter sitting with it, right? So that is on the server or maybe where your actual binary is running on receives an equitable share of available capacity. So let's say this this particular instance has maybe 10 GCU. So all the traffic that comes to it, like from different client, let's say it gets traffic from three different client A, B, C. So all the three client three clients have equal share of the resource or the capacity that this particular instance has. So this prevents a single abusive or high traffic client from consuming the entire quota or like starving the other. This makes well behaved clients on that specific node. Obviously, we can have different set of quotas set for each of the client. Maybe this the quota for A could be 30 and the B could be 30 and the rest 40 could be with C. Now let's talk about the global fairness. So global fairness is more of like enforcing across all the instances. So it could be at a global level where this could be, or this could be at mostly like at your API gateway or at your load balancer. So this global fairness, yeah, or maybe rate limiter. So this rate limiter that sits at the global level, it enforces across all the instances in a distributed system, like in a cluster wise. So also it requires a central service, which again that's why we it mostly sits on the API gateway or the load balancer side, and sometimes it uses a Redis to track the global state, like what all what all different instances has the have the current quotas look like. So it's more complex to deploy and maintain due to the need for a central or highly available store, and it's but it is also more accurate sometimes. So in practice, many system uses local rate limiting because it is a coarse grind and it is high performance because it's the first line of defense. Sometimes relying on local fairness to get a coverage of good enough across millions of users, especially when the traffic distribution to instances is relatively even, is good. And having local fairness is easier to implement and maintain as well, and it has less overload. So let's also talk about what are the different algorithms that rate limiting implements. So as far we know that rate limiting is like it should be the default for any public facing API, because obviously you might have seen as well on Instagram when you try to update your feed too often, you might see some bad requests, or maybe like you'll see too many requests and maybe you'll ask to stop or retry after some time. So simply like too many requests, you need to stop. So this tells the client that hey, it's not me, it's you. Slow down and try again later. Also, there are some rate limiting algorithm that we use. Some of them are like token bucket. Then we have leaky bucket, and we have fixed and sliding window algorithm for implementing rate limiting. So token bucket, we won't be going in detail for these algorithms. We can cover this in a separate video. But talking about token bucket, imagine it as a bucket that get fills with token. Token is simply, you can imagine it as a this to the token allows a request to pass through, right? So imagine there's a bucket of token filled in. These are the tokens, and these are getting filled at constant rate. So whenever a request comes, it if this bucket has a token, it will consume that token. It will consume the token and will be passed on to the your system to process. If there are no token, requests will be dropped. It's as simple as that. And where is a leaky bucket, request enters a queue. We maintain a queue here in the leaky bucket. As soon as the request enters a queue, and this queue has a maybe a fixed size, or maybe or more simpler would be just to imagine it as a bucket which has a hole inside. It has a hole inside, and the requests are whatever number of requests you fill in it, the output will be constant, the constant rate. So it helps to smooth the traffic because the requests are now processed at a constant rate. Whereas we have fixed and sliding window approaches as well, which is like counting requests per minute. So it could be simple. There could be requests from different clients, but during a fixed window of time, let's say time t to time t plus 5, or maybe let's say 5-second window, we only allow 10 requests, which is 10 requests per minute or per 5 second. And the sliding window is like more of a dynamic approach where you can have more control of fine coast control over the number of tokens that you allow within a window, and you can increase and decrease based on the current traffic on your system. Okay, now let's talk about load shedding. Uh, this is where the engineering gets interesting. Load shedding is like a break glass in case of emergency mechanism. So if your rate limiter fails, let's say there was a legitimate traffic and maybe could be a very high spike, maybe could be during a sale or let's go during a Black Friday sale. Load shedding will save your database and CPU from death. So most of the time when a request get throttled, the server sends a 503 status code saying service is unavailable. Client, right? So the question could be, how does the server decide when to throttle a request, right? Let's say there could be a very high spike in the TPS, and now all the request that comes after it, let's say this is your line, this is our line where after which we will shed all the traffic, right? So how will we decide when to throttle? So unlike rate limiting, which uses quotas to decide which client to throttle or maybe which client to stop from abusing, or simple quota enforcement, which is nothing but client isolation, load shedding looks at the health of the service. So the server constantly monitors the signals. So load shedding, most of the cases it sits within your server in the node as a sidecar. This could be a server throttler. All the code sits here. And whenever a request comes, it decides based on the server health, like CPU utilization. This is the very most common sign. The very first is the CPU utilization. So let's say if your CPU is greater than 80%, the utilization is more than 80%, and we have set this saturation point that anything above 80%, we can safely say, yeah, our CPU is getting throttled. So we'll reject all the new requests immediately. So all the requests after this will be load shedded. The second is your in-flight in-flight request. So okay, let's talk about first what are in-flight requests. So in-flight request is specific state of an API call. Let's say you made an API call to a service. So simply what happens is simply it is a request that has been received by the server but has not yet received a response. So let's say this is your server and there's a request, and before this there's a queue which maintains all the requests, and one by one this requests are made out of this queue to put in a ready state or where server can actually acknowledge this request to start processing. So it is currently in the air, which means processing somewhere inside your system. So or maybe let's imagine it this way, that imagine a waiter in a restaurant. The request is the customer hands the waiter an order, right? You made a order. The customer said, okay, I want 3 pizzas. So this order is a request that you made to the restaurant. So the time between the waiter taking the order to the kitchen and the chef cooking the food and the waiter walking back to the table is called in-flight, right? And completed is when the food is placed on the order, which means the response has been generated back. Response. So I hope this is clear now. So in technical terms, a request is considered in flight from the nanosecond the load balancer or the server accepts the TCP connection until the final response is sent back to the client. You can also estimate the average number of in-flight requests using a simple formula. So we can say L is the number of in-flight requests, or it could be simple concurrency. In-flight request or concurrency is nothing but lambda into W. Lambda is request per second, or it could be query per second, your QPS. And W is the average time to handle one request, which is nothing but your latency, right? So, example, if your server can handle 100 requests per second, or let's say 100 QPS. Each request takes, let's say, zero point 0.5 seconds to process. You will have an average of 50 requests in flight, right? Which is nothing but the multiplication at any given moment. Also, in-flight requests are the primary driver of dynamic memory usage in your backend application or systems. A system that does not consume memory just because it exists, it consumes memory because it is doing some work. And every single in-flight request requires a slice of RAM or memory to exist. Obviously, it will sit somewhere because it has some data within it that needs to get processed. Yes. So now, as we know, in-flight request is also one of the key factor that the load balancer, or you can simply say these are the different load trackers. Load trackers. One load tracker is the CPU utilization graph you can simply see, and the in-flight request, how many in-flight requests are basically waiting to get processed, right? So this is a traffic which is still pending to be processed. And then the other could be the memory or the resources, right? And it makes obvious if your memory utilization is around 90% and above, it means we really don't have enough memory for the other request to process. And these and again, if we go in depth, we'll see much more much more complexity and advancement in it. So now we know that load shedding is just simply shredding away, or like terminating or dereferral of non-critical request that will prevent our system from overloading. And the ultimate goal is to our server should never die. It should be always alive, even. And we are fine with processing low QPS, right? Low QPS. But on the contrary part, our systems are not dead. We are still able to manage some of the request. And why it is necessary, we know, because during spikes there will be resource exhaustion. Too many requests consume CPU, memory, and network bandwidth, and it can lead to cascading failures as well, where one server can can l- can bring down all the dependent, or maybe the other services, the dependent services can be overloaded. Let's say service B, service A, and if it goes down and the service B is dependent on it, obviously it will go down because service B might experience high latency in the requests. Hence, the overall performance is degraded. Now let's see what are some real world application of load shedding. And as we know, you might have noticed it. Like let's say on e-commerce platform, some of the critical CUJ, customer usage journey, will be the checkout, right? Checkout, PIM processing, inventory management, and some non-critical would be some product recommendation, reviews, and some wish list, or maybe starting some product during Black Friday sales. Some non-essential feature might be temporarily disabled to ensure that the checkout system or the critical paths remain same. So now, as we know that load shedding is a very proactive way to handle the traffic surge by monitoring request volume, prioritizing critical function, and gracefully degrading non-essential request. And as we know, any request can be represented in any four form: critical, critical plus, shredded, and shredded plus. Critical critical plus is the highest criticality of any request. Like how critical is that request? It could be like authentication, like in any cloud API, it could be authentication, billing, or some core compute services. And non-critical could be like shredded plus, like logging, matrices, or maybe some secondary APIs, or maybe like some health check APIs. Or in terms of social media, the non-critical would be like counts or suggestions, like post suggestions or friend suggestions. And critical path could be posting content, direct messaging. These could be like critical. Shredded plus, as in keep, yeah, shredded is the lowest quality of request, and critical plus is the highest quality of request. And every system need to determine which request we can throttle first. Also, some consideration is that we can, when we do this load shedding, we can always implement retries for shredder request. Like client can implement retries for the shredder request with exponential backup that we already discussed, and we can also have circuit breakers to fail fast when dependencies are struggling. Okay, so before we wrap up, let's use this mental model to distinguish between the two. So rate limiting is all about policy or fairness, or basically the business logic, and it protects the service from abusive server DDoS, specific abusive server, abusive clients, which is nothing but client isolation. We isolate an abusive client from the other clients so that everyone has a fair part of the server, and it happens before the request does any heavy lifting. It is mostly, as we discussed, it mostly at the API gateway or the load balancer level, and the goal is to prevent one user from starving the other. And then load shedding. This is all about survival. Never let your server die. We try our best to protect this service from a global collapse, and it happens mostly inside the service where the server or your binary lies at your pod level. And the goal is to keep the service running, even even if it means dropping the traffic. We are fine to serve low QPS, but we are not fine to go our server crashing. So whenever this question comes, when to use rate limiting and when to use server throttling, this we should ask this question. When so rate limiting asks who are you and how much have you used? Basically your quota. Rate limiting says who are you and how much have you used, which is quota. And based on this question, we decide whether to acknowledge the request or reject the request based on the quota. And load shedding says, and it's asked this question: Am I healthy? Am I healthy enough to accept this request? So if the answer is yes, and I'm healthy enough and I can take few more extra QPS, then it's good enough. The request will be passed on, it will be acknowledged and processed. In the other case, the service will throw a 503, and then the client can obviously do some retry mechanism to retry after some time. By the time the auto scaling system will kick in and do some extra work to lift up the service by doing some horizontal scaling. So that was all, and thank you so much if you have watched till in the end. And if you have any questions, any doubt, or any clarity, or anything that you feel was not correct or could have been added, please add in the comment. Thank you so much. See you in the next one.